We will never truly explore the ocean. Full documentary. Under the ocean's surface, a world older than human memory stretches into endless darkness, where sunlight never reaches and pressure crushes as surely as time itself. Mountains of rock, trenches deeper than the tallest peaks, and currents that have flowed unchanged for millennia conceal life forms that defy imagination. Our machines glimpse only fragments. Our instruments falter in the weight of the abyss. And yet the ocean's mysteries persist, immense and unyielding. This is a realm where exploration is provisional, understanding fleeting, and the unknown absolute. Step into the depths, where the journey is as infinite as the sea itself. The surface, illusion. The ocean's surface seems familiar, but gentle swells and sunlight conceal a vast, inaccessible world governed by physics and biology beyond human perception. Surface waves appear predictable, but they affect only the top centimeters of a 3,700-meter deep ocean, barely registering in the calculations of its mass and power. Tides move vast amounts of water along coasts, yet even these forces have little effect on the deep ocean, showing how limited the human perspective truly is. Beneath the surface, temperature and salinity reshape the ocean as the thin, warm upper layer hides cold, nutrient-rich waters below. Solar radiation penetrates the first few meters with substantial energy, heating the upper ocean far more rapidly than the layers beneath, generating temperature gradients that control everything from plankton productivity to hurricane formation. Argo instruments show seasonal variations in the upper ocean, while deep waters stay at 2-4 degrees Celsius, highlighting a thermal divide invisible from shore. These measurements demonstrate that what appears unified and serene from the surface is, in reality, a stratified system governed by thermocline boundaries that even modern submersibles struggle to traverse efficiently. Far below the sunlit waves, phytoplankton like Prochlorococcus thrive, absorbing vast amounts of CO2 and shaping global climate. Although the surface appears tranquil, satellite imaging shows swirling blooms stretching over thousands of square kilometers, formed by upwelling currents and nutrient pulses that seldom reveal themselves through visual changes on the water's surface. Studies using hyperspectral radiometers reveal that these blooms can reduce atmospheric CO2 by measurable fractions during peak productivity seasons. Yet, the biological forces behind these fluctuations remain hidden beneath a layer of water so opaque to the untrained eye that most observers never realize how dramatically life is reshaping the world beneath them. The surface, therefore, serves not as an entry point to understanding the ocean, but as a barrier concealing interactions so profound that they determine planetary habitability. Drifting just beyond the reach of coastal observation, the surface becomes a highway for organisms whose movements both rely upon and alter surface conditions. As species like the Portuguese man-o'-war, Physalia physalis, and the goose barnacle, Lepus anatifera, depend entirely on the interplay between currents and wind to guide their life cycles. These organisms form complex microsystems on floating debris, from abandoned fishing gear to naturally occurring pumice rafts, creating ecosystems that can cross entire ocean basins while leaving virtually no visible trace from above. Recent studies using satellite-tracked drifters have shown that surface currents like the North Pacific Gyre can hold debris in slow-moving rotations for decades, creating ecological zones that exist entirely apart from the natural boundaries humans typically perceive. Such mobile habitats underscore how the ocean's surface hosts biological communities that slip unnoticed across continents, reinforcing the idea that even the most visible layer resists complete understanding. Moving offshore into the open ocean, the surface becomes the domain of forces so massive that they dwarf all human attempts to comprehend them. As the interface between atmosphere and sea fuels, a continuous exchange of moisture, heat, and energy that drives global weather patterns. Evaporation from the surface contributes approximately 86% of global atmospheric moisture, feeding storm systems that grow into monsoons, typhoons, and hurricanes. Yet these monumental atmospheric phenomena remain largely unaffected by the unseen physics of the deep ocean that lies just beneath. Oceanographers analyzing flux data from buoys in the tropical atmosphere ocean tower ray have found that small fluctuations in surface temperature, sometimes as little as 0.3 degrees Celsius, can trigger events like El Niño, altering global climates for years. Yet these influential changes belie the incredible stillness of the abyss beneath them, where water masses remain unchanged for centuries. The very forces that appear powerful and dynamic from the surface reveal how fragile and thin our perspective is when compared to the ocean's true depth and magnitude. Venturing farther from land, the surface becomes a shifting mirror that hides the world's largest unexplored terrain. As acoustic surveys taken during the last 2 decades show that only about 25% of the global seafloor has been mapped at high resolution, leaving the vast majority of the ocean's physical structure unknown despite the apparent accessibility of its uppermost layer. While satellites equipped with radar altimeters can detect variations in sea surface height caused by underwater features like seamounts and ridges, their signals are too coarse to reveal most deep formations, meaning the surface reflects only hints of the extraordinary landscapes that lie beneath. Scientists working with the Seabed 2030 project estimate that at the current pace of mapping, humanity would require centuries to achieve a complete high-resolution model of the ocean floor, demonstrating that even with advanced instruments, our interaction with the ocean remains painfully superficial. This mismatch between technological reach and environmental scale exposes a fundamental truth. The surface, which seems like an inviting threshold, is in reality the boundary of an inaccessible universe. What begins as a familiar sheet of blue water eventually becomes a misleading promise of accessibility, because every ripple, reflection, and color disguises the complexity that lies just beyond the human gaze, allowing people to believe that the ocean is a place that can be understood from its shimmering exterior. The impression of clarity created by calm seas and luminous horizons masks the intricate webs of life and physics that operate beneath. And as sunlight fades into deeper layers of water, the true character of the ocean begins to reveal itself as a realm defined by obscurity rather than transparency. The illusion dissolves slowly as one contemplates the vast chasms, unseen creatures, and hidden forces waiting below the threshold where light can no longer penetrate. With every meter fallen into the quieting blue, the descent into deeper waters exposes a world that grows increasingly alien, drawing us gently away from the comfort of the surface and toward the mysteries that gather in the darkness below. Into the blue veil, a faint dimming of color becomes noticeable as the body sinks past the threshold where surface brightness begins to diffuse, because even the slightest descent introduces the first hints of a world that no longer behaves according to familiar terrestrial rules. The shimmering reflections that once conveyed a sense of clarity now break apart into muted gradients, revealing how quickly water absorbs and scatters wavelengths of light, starting with the longest reds and oranges that vanish within the first 10 meters and leaving blue as the dominant survivor of the photic spectrum. This transition sets the stage for a realm where visibility decreases not as a gentle fade, but as a steep collapse, turning daylight into a fragile visitor that cannot follow much farther. A gradual cooling of the surrounding water accompanies this fading illumination, marking the start of environmental changes that intensify with each passing meter. The upper photic zone, which supports nearly half of Earth's oxygen through the photosynthetic activity of phytoplankton, rests on a knife edge of conditions requiring stable sunlight, narrow temperature ranges, and predictable nutrient flows. The moment those parameters shift, even slightly, the microscopic drifters respond instantly, thinning in density as available light diminishes and altering the structure of life in a column that stretches kilometers downward. A sense of narrowing space emerges as suspended particles, known as marine snow, drift past in slow, deliberate motions, forming a continuous storm of organic debris that feeds countless species adapted to this vertical highway of falling nourishment. The composition of these particles, sheddings of gelatinous zooplankton, discarded larval casings, excreted waste pellets from copepods, reveals the recycling engine of the ocean, where almost nothing remains unused for long. These drifting materials help sustain midwater hunters, such as Chauleodus sloani, the Sloane's viperfish, which lurks in the dimming columns, even at depths where sunlight still threads through but begins to lose its dominance. An increasingly spectral atmosphere develops as scattering light interacts with suspended organisms, possessing reflective tissues or microscopic lenses, making the water shimmer with fleeting flashes of silver and opal. Many of these creatures belong to groups like comb jellies, whose ciliary rows diffract the remaining blue wavelengths into iridescent rainbows despite their delicate, nearly invisible bodies. These displays do not arise from intentional signaling, but from the physics of refraction in a medium where every movement bends and fractures the last remnants of daylight. A shift in pressure asserts itself more forcefully with continued descent, because even within the upper 100 meters, the increase becomes far greater than anything experienced on land. Every 10 meters of depth adds roughly one additional atmosphere of pressure, compressing gases, slowing cellular activity, and forcing organisms to evolve flexible membranes, reduced internal air spaces, and biochemical pathways that can withstand crushing forces. Species like the lanternfish, belonging to the family Myctophidae, demonstrate these adaptations with bodies structured for energy-efficient vertical migrations that span hundreds of meters each day, rising at night to feed and retreating by dawn to avoid predators. A softening of sound replaces the visual clarity lost earlier, because water transmits low-frequency vibrations with astonishing efficiency, allowing distant calls, volcanic rumbles, or ship engines to reverberate through the column. Whales navigating across ocean basins rely on this conductive quality, using infrasonic signals that travel thousands of kilometers with minimal loss of energy. Yet as depth increases, the soundscape changes dramatically, filtering frequencies and creating layers of acoustic shadows where certain tones become trapped or redirected, forming the enigmatic deep sound channel that bends audio waves along a curving path through the ocean's interior. A steady metamorphosis of locomotion becomes evident among midwater species that rely on gelatinous bodies, elongated fins, or complex musculature shaped by the viscous drag of denser water. Creatures like the heteropod mollusks propel themselves with wing-like foot structures, generating slow, rhythmic undulations that minimize energy expenditure in a region where every calorie is precious. Even fish adapted for higher speed bursts, such as Alipocephalus australis, possess streamlined profiles that allow them to navigate shifting currents with precise efficiency in a world governed by buoyancy rather than gravity. A deepening sense of remoteness emerges as the last wavelengths of sunlight surrender to darkness between 150 and 200 meters, forming the upper boundary of the dysphotic, or twilight, zone where photosynthesis becomes impossible and biological strategies shift towards stealth and predation. Bioluminescent organs, known as photophores, begin to dominate the visual landscape, illuminating bodies with constellations of blue-green points controlled by neural or chemical signals. These light-producing structures, found in countless species from hatchetfish to siphonophores, serve purposes ranging from camouflage and communication to prey attraction, each governed by biochemical reactions involving luciferins and luciferases. A sense of altered gravitational orientation accompanies this fading light because, without solid reference points or reliable visual cues, organisms evolve sensory organs capable of detecting pressure gradients, electrical fields, or chemical trails. The lateral line systems of fish become increasingly sensitive, enabling them to orient themselves within unseen currents or to detect the approach of predators moving through the water's subtle vibrations. Invertebrates like the glass squid Toithoenia pellucida employ statocysts, fluid-filled balance organs lined with sensory hairs to maintain stability in their expanding liquid surroundings. A gradual quieting of human assumptions settles in as the descent continues, because every shift in physics, chemistry, and life demonstrates how unfit the human body and technology are for even modest journeys into the midwater realm. The rapid disappearance of light, the exponential rise of pressure, the reorganized rules of sound transmission, and the vast reconfiguration of biological strategies all reveal a world so foreign that the familiar concepts of exploration lose meaning long before true depth is reached. The water grows darker, colder, and more enigmatic with every meter, gently steering thought toward the recognition that this twilight boundary is not an endpoint, but merely the beginning of a far stranger domain waiting below, where the last hints of daylight vanish entirely, and the ocean reshapes itself into something increasingly distant from human comprehension. Kingdom of the Twilight Zone. Descending into the mesopelagic, darkness does not mean stillness. Sunlight gives way to a realm of continuous motion. Temperature layers concentrate zooplankton, midwater fishes, and gelatinous drifters, each finely tuned to pressure, light, and energy scarcity, creating a pulse of life invisible to human eyes. Small changes in depth reveal populations with different eyes, metabolisms, and buoyancy, finely tuned to pressures dozens of times greater than at the surface. What appears barren to untrained eyes is, in fact, a domain structured around density pulses, faint optical cues, and the steady pulse of bodies rising and falling through a dim world that few humans ever truly visualize. Billions of mesopelagic organisms surge upward nightly, moving hundreds of meters to feed near the surface before retreating into darkness. This phenomenon, known as diel vertical migration, involves species such as cyclothone, the bristle-mouthed fishes, whose collective mass may exceed that of any other vertebrate lineage on Earth, and whose ascent and descent alter local carbon chemistry and nutrient flows on a global scale. Acoustic instruments show vast sheets rising uniformly, redistributing energy from surface waters to deeper zones with remarkable consistency. The sheer magnitude of this migration, repeated every 24 hours across all the world's oceans, reveals a moving engine whose cycles and interactions dwarf any ecological rhythm experienced on land. Glittering chains of bioluminescent pulses thread through the dim water, produced by species whose light-based languages remain almost entirely undeciphered despite decades of deep-sea observation. Many signals come from photophores with bacteria or chemical reactions, emitting light precisely tuned to deep-sea optics. Small crustaceans emit rapid defensive flashes that unfold like sparks breaking from a grinding wheel, while midwater fishes use narrow beams along their ventral surfaces to perform counter-illumination, matching the brightness of residual light above to render themselves nearly invisible to predators lurking below. Siphonophore colonies coordinate hundreds of zooids to create cascades of light extending meters, forming some of the longest bioluminescent organisms. Drifting in immense, slow-moving columns, the lanternfish populations dominate this zone with a biomass greater than that of all the world's fisheries combined, shaping the distribution of predators and prey across thousands of kilometers. Lanternfish have species-specific photophores and multi-layered retinas sensitive to faint light. Stable isotope analyses reveal that lanternfish feed on a wide variety of mesozooplankton, gelatinous organisms, and small crustaceans, drawing energy from sources that fluctuate seasonally and regionally but remain abundant enough to support their staggering numbers. Dense shoals form thick layers in the deep scattering layer, once mistaken for the seafloor. Rival predators rise from deeper shadows, including long-fanged snaggletooths and swift-bristled barracudinas, equipped for ambush in near-perfect obscurity, each one sculpted by evolutionary pressures that reward stealth and energy efficiency. Snaggletooths have hinged jaws that open wide, letting them swallow prey nearly their own size. Barracudinas use elongated, lightweight bodies to strike rapidly despite dense mid-water drag. Gelatinous predators such as Atolla jellyfish and colonial siphonophores also patrol these depths, relying on trailing tentacles and neurotoxic stings that compensate for the low visibility and slow maneuverability typical of organisms in this pressurized realm. Sweeping currents carry suspended nutrients in delicate ribbons, creating patchwork feeding grounds that change location and density with every passing hour, largely dictated by the shifting thermocline and the movement of internal waves. Nutrient ribbons carry marine snow detritus, plankton, and fecal pellets falling steadily from the surface. Marine snow composition varies with productivity, blooms, and dust, marking ecosystem changes across ocean basins. Many mesopelagic animals rely on these sinking particles as both direct and indirect energy sources, shaping trophic interactions in ways that researchers continue to model but have yet to fully quantify. Sensitive acoustic studies reveal complex layers of sound-scattering organisms that shift vertically like living curtains, confusing sonar systems designed to map them, because the density of swimming bodies disrupts sound transmission in unpredictable patterns. These layers can rise and fall by several hundred meters within hours, responding to predator pressure, light gradients, and subtle changes in hydrostatic conditions. Internal reflections caused by bodies with differing acoustic impedance produce false signatures that sonar algorithms often misinterpret as schools of fish, geological surfaces, or even moving seafloor slopes. The variability of these scattering layers demonstrates that the mesopelagic is not simply a band of dim water, but a dynamic acoustic landscape that behaves more like a changing weather system than a static environment. Researchers studying carbon transport point to the mesopelagic as a keystone in global climate regulation, with sinking fecal pellets and exhaled CO2 shaping atmospheric chemistry in ways only recently quantified by biogeochemical models. Diel vertical migration redistributes carbon by moving metabolically active organisms upward at night, where they feed, and downward by day, where they respire and excrete deeper in the water column, enhancing long-term sequestration. Laboratory studies reveal that lanternfish and bristlemouth digestive processes produce dense, rapidly sinking pellets that descend at rates of several hundred meters per day, efficiently transporting carbon to the bathypelagic zone. This transport mechanism, part of the biological carbon pump, influences how much CO2 remains trapped in the ocean versus released back into the atmosphere, linking mid-water ecosystems to global climate cycles. New technologies attempting to capture this world, autonomous gliders, deep profiling floats, and low-light cameras, manage only fragmented glimpses of an ecosystem too vast to quantify, because visibility remains severely constrained by light absorption and scattering at these depths. Even the most advanced imaging systems struggle to track fast-moving organisms whose bodies lack strong optical contrast, while nets used for sampling often miss fragile, gelatinous species that collapse upon contact. Acoustic sensors provide broader coverage, but still fail to detect smaller or softer-bodied organisms that do not reflect sound efficiently, leaving large portions of the ecosystem effectively invisible to human monitoring. The result is that biomass estimates vary by orders of magnitude, demonstrating how little certainty exists regarding even the most fundamental measurements of this enormous realm. A growing recognition settles in that this twilight realm, vibrant and immense yet largely invisible, represents both a frontier of discovery and a reminder of how little control or comprehension humanity truly possesses as the descent continues toward deeper obscurity. Because the darkness that now thickens around these drifting shoals signals a world where familiar rules dissolve even further. The faintest hints of remaining daylight fade into a muted glow that will soon vanish completely, and the silhouettes of migrating creatures slip gradually into forms that appear more imagined than real. The deepening shadow marks a threshold that countless species cross with ease, yet remains nearly unreachable for human presence. And as the journey sinks toward the next gradient of darkness, the ocean begins to shed the last traces of twilight, preparing to reveal the far stranger territories that wait below, where darkness begins to rule. As the last vestiges of dim light fade entirely, a new reality asserts itself, where pressure and silence govern every motion, and the once familiar rhythms of the upper layers are replaced by a lethargic, deliberate pace of existence. The surrounding water presses inward with relentless weight, every 10 meters adding another atmosphere, until hundreds of times the force at the surface compresses every cavity, reshaping anatomy and behavior alike. Organisms that survive here have abandoned the rigid structures of shallow seas, trading speed and power for flexibility, density-tolerant tissues, and metabolic systems calibrated for extreme efficiency. Shadows lengthen not because of light, but because of the ocean's own density, forming a landscape that is simultaneously vast and intimate, where every movement is calculated and every encounter rare. Here, water density climbs to extremes, compressing gas-filled structures and sculpting bodies in ways impossible near the surface, demanding evolutionary creativity in every aspect of life. Deep-sea fishes have replaced air bladders with lipid-filled sacs or reduced internal cavities to resist collapse, while squids and gelatinous invertebrates rely on near-neutral buoyancy to drift silently through the abyss. Cellular membranes incorporate unsaturated fatty acids to maintain fluidity at near-freezing temperatures, and enzymatic reactions slow dramatically to conserve energy in a habitat where prey is sparse and every calorie matters. Even locomotion is different. Short bursts of speed are more common than sustained swimming, and ambush predation becomes the dominant strategy. Predators appear as improbable silhouettes, their jaws, spines, and teeth exaggerated for a world where encounters are rare but decisive, each strike representing the culmination of evolutionary perfection honed over millions of years. The anglerfish, with its bioluminescent lure dangling from a modified dorsal spine, waits motionless until an unsuspecting prey drifts within reach, consuming animals sometimes half its own size in a single motion. Viperfishes extend hinged jaws that open impossibly wide, while gulper eels inflate capacious mouths capable of swallowing anything foolish enough to wander into their trap. These extraordinary adaptations underscore the extremity of selective pressures that define life far below human eyes and technology. Many inhabitants rely on bioluminescence, but in this near-permanent darkness, light becomes a weapon, a lure, or a cryptic language wielded with precision that can spell survival or death in milliseconds. Photophores dot bodies in intricate patterns, signaling readiness to mate, warning potential predators, or imitating smaller organisms to attract prey. Some deep-sea squid can produce complex flashes or pulses along their arms, communicating within shoals invisible to any observer without specialized instrumentation. Bioluminescence dominates the visual landscape, defining territory, identity, and hunting strategy, transforming the abyss from an empty void into a network of fleeting, luminous gestures. Gelatinous and soft-bodied organisms dominate in numbers, their fragile frames resisting the crushing forces that would obliterate rigid skeletons and allowing them to drift with minimal energy expenditure. Siphonophores and jellyfish extend long, trailing tentacles that ensnare prey with passive efficiency, while deep-sea ctenophores use ciliary rows to glide through water as slow-moving predators. These delicate animals often escape capture by traditional nets, meaning human knowledge of their abundance is still rudimentary, but they form a crucial backbone of mid- and bathypelagic food webs, connecting surface detritus to larger predators and shaping the dynamics of the abyssal ecosystem. Metabolic efficiency is paramount, as scarce food sources demand minimal expenditure and opportunistic feeding strategies, forcing life in the bathypelagic to adopt patience as a survival imperative. Some species, like the gulper eel, can endure months without consuming prey, while others store energy in dense lipid tissues to buffer long periods of famine. Observational studies show that vertical migrations, common in shallower zones, become far more restricted, replaced by strategic ambushes and opportunistic consumption of carcasses that sink from above. Energy budgets dominate every interaction, creating a rhythm that is deliberate, slow, and invisible to the casual observer. The seafloor rises and falls with subtle topography, forming micro-habitats for scavengers and ambush predators alike, as canyons, ridges, and escarpments provide structure in an otherwise featureless darkness. Crustaceans, echinoderms, and polychaete worms exploit these environments, consuming organic debris and carrion in complex spatial mosaics that concentrate life where resources accumulate. These benthic zones serve as reservoirs for both energy and diversity, linking vertical processes in the water column to horizontal dispersal across thousands of kilometers. Pressure-adapted organisms exploit microcurrents and sediment traps, revealing a level of spatial organization invisible from the surface, yet critical for sustaining life at depth. Temperature stabilizes near freezing, slowing biochemical reactions and shaping growth rates across species with remarkable uniformity, while oxygen concentrations reach critical minima that constrain distribution and activity. Specialized hemoglobins and gill structures allow some fish to survive where oxygen levels would be lethal elsewhere, and mitochondria within muscle tissues operate at minimal energy outputs, sustaining locomotion under extreme scarcity. These physiological innovations are coupled with behavioral strategies such as reduced competition and opportunistic scavenging, allowing populations to persist in a realm seemingly inhospitable to life, yet astonishingly abundant in its own terms. Attempts to capture this realm with cameras, submersibles, and sensors reveal only fragments, each glimpse emphasizing the inaccessibility of the deep abyss, because the pressures and darkness make prolonged human presence nearly impossible. Robotic vehicles can descend thousands of meters, but their range, endurance, and sensory capabilities remain limited, while observations are often biased toward larger or more conspicuous organisms. Indirect sampling through acoustics or baited traps provides partial information, but cannot capture the full richness of the community, underscoring the fact that humanity's understanding of the bathypelagic remains partial, episodic, and mediated through fragile technology. In this world where darkness rules unchallenged, the interplay of extreme physics, biological ingenuity, and evolutionary artistry offers both revelation and a profound sense of human limitation, because even the most advanced instruments can only hint at the true scale and diversity of life. Silence dominates, broken only by the faintest mechanical hum of distant submersibles or the occasional echo of falling debris. Yet each shadow, each flicker of bioluminescence, tells a story of adaptation beyond surface comprehension. Pressure, cold, and scarcity shape everything from skeletal form to feeding behavior, and as the descent continues, the observer begins to sense that below this layer, a deeper, more permanent darkness awaits, one where life persists in forms so alien that human understanding can only aspire to glimpse its patterns, forever tantalized by the mysteries of the abyss. The stillness of the abyssal plains. Beyond the last traces of bathypelagic movement, the ocean floor opens into an endless expanse, a realm defined by patience and stillness, where horizons stretch beyond perception, and the faintest ripple of life goes almost unnoticed. Here, the water above seems suspended in quiet permanence, and the abyssal plains themselves appear as sheets of muted grey, sculpted by forces too slow to observe within a human lifetime. Every metre of this vast landscape is a record of time's imperceptible hand, a testament to sedimentation and tectonics acting on scales that dwarf the brief flicker of human presence. In this place, motion is subtle, measured, and almost reverential, as if the ocean itself demands silence to preserve the magnitude of its hidden history. Sediments settle over millennia, layer upon layer, recording ancient currents, microscopic life, and the faint echoes of distant eruptions, building a stratigraphy that can reveal climatic cycles, glacial advances, and shifts in ocean chemistry over tens of millions of years. Fine clay, silt, and organic debris accumulate at rates as slow as 1 to 2 centimeters per 1,000 years, each particle a fragment of a surface ecosystem that once existed far above. Radioisotope dating and deep-sea coring techniques allow scientists to reconstruct these timelines, demonstrating that what appears empty is, in fact, a rich archive of planetary change, meticulously preserved beneath the weight of the ocean. Occasional benthic invertebrates traverse these plains with deliberate slowness, leaving trails that mark the only visible motion across a vast, muted canvas. As brittle stars extend delicate arms and holothurians propel themselves with soft, undulating contractions. Polychaete worms probe the sediment for nutrients, while occasional deep-sea crabs scavenge fragments of organic matter. These creatures move with extreme economy, their behaviors dictated by the scarcity of resources, and their presence, though rare, punctuates the monotony of an otherwise motionless world, reminding observers that life persists even in the quietest reaches of the ocean. Tectonic shifts rise imperceptibly beneath the sediments, shaping hidden ridges and subtle valleys that guide water movement and nutrient deposition, creating microenvironments that are otherwise invisible within the uniformity of the plains. Abyssal hills, fractures, and faulted escarpments form a patchwork of subtle topography across thousands of square kilometers, influencing the flow of deep currents and the deposition of sediments. These features also determine the distribution of benthic communities, concentrating organic material in low areas and offering anchorage or shelter in regions otherwise devoid of structure. Sparse organic matter filters down from above, sustaining communities whose adaptations emphasize energy efficiency above all else, as detritus slowly rains from the sunlit zones hundreds or thousands of meters overhead. Microbial mats and scavengers rely on this intermittent influx, consuming marine snow, fecal pellets, and fragments of carcasses that manage to reach the seafloor intact. Laboratory experiments and deep-sea observations reveal that the rate of decomposition and energy transfer in these conditions is extraordinarily slow, stretching survival and activity cycles to timescales unimaginable near the surface. Chemical gradients in oxygen, sulfide, and methane carve invisible niches, forming microhabitats that support specialized, enigmatic life, including chemosynthetic bacteria and rare tube worms that colonize small hydrothermal seeps or methane-rich pockets. These pockets are oases in an otherwise monotonous expanse, providing concentrated energy sources and driving localized biodiversity that belies the apparent emptiness of the surrounding plains. Even within the uniformity, small-scale chemical and thermal variation shapes the biology of every organism, demonstrating that subtlety governs survival in these extreme conditions. Sediment cores reveal a slow history of planetary change, from glacial cycles to tectonic rearrangements, preserved in grains too small to see without magnification. Each stratum a frozen narrative of shifting continents, fluctuating sea levels, and millennia of ecological transformation. Analyses of mineral composition, isotopic ratios, and microfossil content provide windows into oceanic productivity, atmospheric chemistry, and the migration of species across ancient seaways. These cores show that the abyssal plains, though seemingly empty, act as the planet's silent record keepers, documenting events that shaped life above and below for eons. Rare bursts of activity punctuate the silence, a feeding frenzy around a fallen carcass or the fleeting glow of a bioluminescent organism, illuminating the immediate darkness. Whale falls, for instance, trigger rapid colonization by scavengers such as hagfish, crabs, and amphipods, creating temporary oases that sustain highly specialized communities for decades. Even a single carcass can influence local chemistry, nutrient distribution, and population dynamics, providing a stark contrast to the surrounding stillness and illustrating the episodic nature of life on the abyssal plains. Despite the emptiness, abyssal plains play a critical role in global biogeochemical cycles, storing carbon and moderating nutrient flows on a planetary scale. Organic matter buried in sediments contributes to long-term carbon sequestration, while microbial decomposition transforms nutrients into forms accessible to other deep-sea life. These slow, cumulative processes regulate the chemistry of the ocean over millennia, subtly connecting the deepest, quietest regions of the Earth to the rhythms of climate and the biosphere above, revealing that stillness does not equate to insignificance. Amid the ocean's silent expanse, it speaks in geological time, hinting at the hidden hotspots and hydrothermal eruptions that punctuate the darkness with sudden drama, because even the most monotonous stretches are intersected by forces of energy and heat capable of transforming local ecosystems in moments. Sediments may conceal volcanic vents, mid-ocean ridges, and tectonic fissures, each with its own localized communities and chemical anomalies, standing as reminders that beneath the apparent calm lies a potential for sudden, transformative change. The abyssal plains, immense and patient, cradle these mysteries, bridging silence and the occasional eruption of vitality, guiding the observer toward regions where geology, chemistry, and biology converge in startling, often explosive clarity. Volcanoes in the dark. From the monotony of the abyssal plains, heat and light erupt in unexpected pulses, revealing islands of activity in the dark, where the cold, still water gives way to fountains of superheated minerals and chemical energy. Chimneys of black and white smokers rise from fissures, sculpted over decades as molten rock interacts with seawater, forming towering columns whose surfaces glint with metallic deposits. These hydrothermal structures are ephemeral yet enduring, born in sudden geological convulsions and gradually eroded by the relentless current, shaping habitats that are as volatile as they are productive, offering a fleeting glimpse of life, thriving amid chaos. Minerals dissolved in a superheated water stream from fissures, carrying iron, manganese, copper, and sulfide compounds that precipitate upon contact with the near-freezing abyss, layering new surfaces for organisms to colonize. Temperatures within the vent fluids can exceed 400 degrees Celsius, yet only a few meters away, water remains near 2 degrees Celsius, creating gradients so steep that life must be finely tuned to exploit this narrow band of habitability. These chemical eruptions are both creators and destroyers, generating complex terrain and energy sources while displacing or incinerating any organism caught too close, demonstrating the precarious balance that governs survival in this volatile microcosm. Communities of vent-adapted species cluster around these chemical oases, thriving in concentrations and temperatures that would annihilate shallow water organisms, forming ecosystems entirely independent of sunlight. Dense aggregations of tubeworms, mussels, clams, and shrimp occupy the periphery and summit of chimneys, their survival dependent on symbiotic bacteria that convert sulfide-rich fluids into usable energy. Microbial mats shimmer along mineral surfaces, invisible to the human eye, but forming the base of an intricate food web where predators and grazers rely on chemosynthetic productivity rather than photosynthesis, creating an ecosystem that exists by an entirely alien logic to surface observers. Giant tubeworms anchor themselves in mineral-rich substrates, their red plumes housing chemosynthetic bacteria that oxidize hydrogen sulfide into energy, fueling growth at astonishing rates compared to surrounding abyssal life. Clams and mussels harbor similar bacterial symbionts within specialized gill tissues, converting chemical energy into sustenance that supports reproductive and defensive activities in extreme conditions. These relationships demonstrate an evolutionary ingenuity that allows life to flourish under crushing pressures, near freezing temperatures, and near total darkness, a feat impossible for surface-adapted species, where even minor disturbances can ripple through the local community in ways both subtle and dramatic. Vent fluids, laden with sulfides and metals, swirl into the cold abyss, forming plumes that extend meters into the surrounding water column, slowly diffusing their heat and nutrients while influencing microbial and animal distribution. Observations using ROVs reveal delicate layering of fluid jets, each supporting different assemblages of organisms adapted to specific temperature and chemical ranges. The turbulence and mixing create a constantly shifting mosaic of habitable niches, where organisms must remain finely attuned to microgradients or risk suffocation, starvation, or thermal stress, emphasizing the dynamic tension between stability and flux in these ecosystems. Predators circle these vent hubs, exploiting concentrated prey in an ecosystem governed by chemical gradients rather than sunlight. From blind crabs scuttling along chimneys to shrimp that navigate by sensing thermal and chemical cues. Vent octopuses patrol the fringes, their limbs extending into microbial mats and filtering out tiny invertebrates, while small predatory fishes lurk in the shadows, drawn by the density of smaller organisms congregating around the vents. These interactions highlight a predator-prey dynamic entirely dictated by resource concentration rather than visual detection, emphasizing the unique evolutionary pressures of hydrothermal systems and the delicate interdependence of species surviving at extremes. Rapid ecological succession occurs as vents collapse and reform, forcing organisms to adapt, migrate, or perish in cycles spanning decades or centuries. Chimneys can topple in seconds due to mineral deposition imbalance or tectonic tremors, smothering communities and forcing survivors to disperse. New fissures may open nearby, allowing colonization to begin afresh. Studies show that species turnover in vent ecosystems is far faster than in surrounding abyssal plains, demonstrating that instability drives innovation, adaptation, and survival strategies in a way alien to surface-dwelling ecologies. In this context, even patience and endurance have limits, as life must respond to geologic events faster than the eye can follow. Thermal and chemical variability creates microhabitats, where subtle differences in temperature, pH, or mineral concentration define life's distribution and abundance, sometimes separated by mere centimeters. Tubeworms dominate high sulfide zones, while shrimp congregate at slightly cooler margins, and bacterial mats extend along gradients invisible to the naked eye. Even slight shifts in vent fluid composition can restructure these miniature worlds, demonstrating how finely tuned adaptations sustain biodiversity under relentless environmental pressure, underscoring how localized forces can create ecological wealth amid pervasive darkness. The geology itself constantly reshapes as eruptions, sediment deposition, and tectonic movement reconstruct vent fields in unpredictable patterns, forming chimneys, fissures, and collapsed valleys that guide life's organization. Mineral deposition can isolate populations or connect them through narrow corridors, while vent collapse resets successional stages, creating a cycle of destruction and renewal that is both violent and life-sustaining. These transformations reveal that the deep ocean is not a static repository, but a dynamic laboratory where chemistry, geology, and biology collide in perpetual motion, reminding us that human observation can only ever capture a fragment of the full complexity. Even the faintest observation by submersibles and sensors cannot fully convey the scale or dynamism of these vent ecosystems, because the interplay of heat, pressure, and mineral flux is constantly reshaping every surface and organism. High-definition cameras, sampling arms, and environmental sensors record only fleeting instants, leaving the majority of activity unobserved and unknowable, a humbling reminder of the ocean's power and humanity's limited reach. The vent systems pulse with energy both destructive and creative, hinting at greater extremes that lie deeper, where sunlight never penetrates, and life persists entirely on forces we can barely begin to measure. Through a dance of chemistry, heat, and life, the deep ocean demonstrates both its capacity for sudden creation and the limits of human observation, because even the most sophisticated submersibles and sensors capture only fleeting snapshots of a system in constant flux. Vent fields flicker in existence like ephemeral cities of life, and the observer senses that the even deeper trenches, cloaked in absolute darkness and immense pressure, await with mysteries no current technology can fully illuminate. Here, on the peripheries of these volcanic oases, the ocean whispers of extremes yet unseen, of ecosystems sculpted by fire beneath the waves, and of the perpetual challenge humanity faces in understanding the depths, inviting descent into even darker and more alien realms. The deep chasms. Past the pulsing vent fields, the ocean folds inward, forming narrow chasms that descend into darkness more absolute than anything above, as if the sea itself had carved secret corridors leading into Earth's hidden underworld. The walls of these trenches rise and fall in jagged relief, coated with sediments that have accumulated over millennia, their surfaces etched by landslides and tectonic shifts too slow to perceive but relentless in their effects. The faint glow of distant submersible lights illuminates only fragments of the terrain, leaving the mind to imagine the immense void beyond the beam, a place where human senses reach their limits almost instantly. These trenches, carved by tectonic collisions and the slow grinding of Earth's plates, plunge kilometers below the abyssal plains, creating some of the planet's most extreme depressions. Subduction zones push one plate beneath another, dragging sediments, rocks, and even entire ecosystems into vertical gulfs of unimaginable depth. The Mariana Trench, reaching nearly 11,000 meters, represents a pinnacle of these extremes, where the seafloor narrows into a labyrinth of chasms, cliffs, and overhangs, and every meter downward amplifies conditions that would obliterate life or technology unprepared for the journey. The narrowness of these trenches concentrates both pressure and environmental extremes, creating a sense of claustrophobic depth that magnifies the alien quality of the Hadal Zone. Pressure rises relentlessly, increasing roughly 1 atmosphere every 10 meters, until even the sturdiest human-made vessel feels as though it could be crushed like glass, a reminder that the Hadal environment is fundamentally hostile. At the base of the deepest trenches, pressures exceed 1,100 atmospheres, compressing equipment, fluids, and even the structural integrity of submersible hulls. Life that thrives here has evolved in these conditions, but humans cannot endure them directly, relying instead on machines that must balance resilience, precision, and delicate maneuvering, each descent a high-stakes test of engineering against nature's extremes. The crushing weight of the overlying ocean also influences the behavior of fluids, sound propagation, and even chemical equilibria, creating a multidimensional challenge for researchers attempting to measure this environment. Submersibles drift silently along the vertical walls, lights piercing only tiny slices of the surrounding black, revealing jagged outcrops, slumping sediments, and rare glimpses of life. Cameras capture ephemeral images of benthic organisms clinging to sheer rock faces or burrowing into silt, their movements slow and deliberate under immense pressure. Every image, every measurement, emphasizes both the richness and the fragility of these ecosystems. And yet the vast majority of the trench remains unobserved, a void that stretches far beyond the reach of human eyes and instruments. Observers aboard the surface ships feel both awe and frustration as they watch instruments struggle against the depth, registering fragments of a world that refuses full illumination. Life here has adapted to starvation, pressure, and darkness. From gelatinous amphipods that drift through the water column like drifting balloons to the ethereal Hadal snailfish, which defy expectations of anatomy and metabolism. Many organisms rely on detritus falling from the layers above, while some scavengers exploit chemical anomalies, capturing energy from sulfide-rich seeps that occasionally punctuate the trench floor. The adaptations are subtle yet profound. Flexible skeletons, reduced musculature, antifreeze-like proteins, and metabolic rates so low that growth and reproduction occur over years rather than weeks, illustrating evolution's patient ingenuity. In some trenches, species exist nowhere else on the planet, highlighting the isolation and specialization forced by these vertical gulfs. Temperature hovers just above freezing, and chemical gradients dictate where organisms can survive, creating fragile pockets of biodiversity amid the monotony of rock and silt. Oxygen minimum zones appear sporadically along trench walls, and organisms must either avoid them or evolve biochemical strategies to tolerate hypoxia. Even minor tectonic activity or sediment shifts can obliterate these pockets, revealing the precarious balance that defines hadal life and underscoring how extreme the margins of habitability truly are in these abyssal voids. Subtle variations in salinity, pressure, and mineral content dictate the boundaries of every species niche, compressing life into narrow ecological corridors along vertical cliffs. Occasionally, seismic tremors awaken the chasms, dislodging sediments and reshaping habitats in moments that outlast human patience by millennia. Underwater landslides cascade down trench walls, burying microbial mats and small invertebrates, while rockfalls create temporary cliffs and crevices that alter microhabitats. Such disturbances illustrate that the deep ocean is not static but continuously sculpted by geological forces, where life must adapt, endure, or vanish, often without a witness to record the transformation. Each tremor is both destructive and creative, demonstrating that evolution in these extremes occurs against a backdrop of constant geological flux. Remote sensors and deep-sea landers record fleeting glimpses, yet each descent emphasizes how little can truly be measured or understood in real time. Pressure-resistant instruments capture temperature, salinity, and chemical composition, while cameras and sonar map small corridors. But every snapshot is temporary, unable to represent the trench in its full dynamism. The interaction between instrumentation and environment underscores a central paradox. Even as technology extends our reach, the vastness and variability of these depths remain overwhelmingly beyond human observation. Communication with surface ships is slow and limited, each pulse of data a reminder of the immense separation between human perception and the ocean's hidden extremes. Signals are delayed, distorted, and weakened by the kilometers of water above, forcing researchers to make critical decisions with incomplete information. Every mission becomes a meditation on uncertainty, where anticipation and risk coexist, underscoring that the trenches are not merely remote, they are fundamentally beyond full human control. Crew members often describe a disorienting sense of intimacy with danger, as if the chasm itself watches and tests each probe that dares intrude. Encased in crushing pressure, the ocean asserts its dominion, whispering that there are realms no machine can fully probe, and mysteries no human mind can entirely grasp, beckoning explorers toward limits that may never be crossed. Even as ROVs skirt jagged walls and cameras illuminate alien landscapes, the true scale and depth of the hadal zones remain out of reach, a shadowed testament to Earth's extremes. The deep chasms, carved over eons, and inhabited by creatures that thrive under conditions lethal to almost all other life, remind us that the ocean contains worlds that exist entirely on their own terms, vast, unforgiving, and hidden, inviting both awe and humility before the limits of exploration, and hinting at the monumental engineering challenges awaiting the next descent into darkness. Machines that break before they reach the bottom. Where light cannot reach, human ambition meets its harshest trial as engineers send fragile vessels into crushing darkness, knowing that every descent is a delicate negotiation with the ocean's immense power. Even the most meticulously designed submersibles face a realm where physics grows unforgiving. Pressure rises by roughly 1 atmosphere every 10 meters, and at the greatest hadal depths, it can exceed 1,100 atmospheres, conditions that would instantly obliterate an unprepared structure. Each dive is a gamble, a dance between engineering ingenuity and the ocean's indomitable laws, where failure is not only probable but expected, and every mission carries the silent awareness of danger. Even the strongest hulls, forged from titanium and reinforced composites, bend and whisper under pressure that would flatten conventional steel, and engineers must anticipate micro-deformations that accumulate silently over time. Every weld, panel, and seam is tested against forces that cannot be replicated entirely in laboratories because the interplay of temperature, pressure, and seawater chemistry at extreme depths produces stresses far beyond surface experience. Hulls may survive initial descent only to fail under subtle imperfections, revealing the razor-thin margin between survival and catastrophe in a world defined by weight and density rather than gravity alone. Historical accounts of early deep-sea experiments remind us that even modest depths once spelled disaster for experimental designs, and those lessons echo in every modern mission. Sensors designed to record temperature, salinity, and chemical gradients often fail mid-descent, succumbing to extreme cold, corrosive mineral content, or the sheer compressive force of water. High-precision instruments, encased in delicate housings, may collapse or leak, while onboard electronics may short under conditions that exceed their design thresholds. Even the most advanced pressure housings for cameras and spectrometers are not immune. Glass spheres may implode, syntactic foam may crack, and optical lenses may fracture, leaving explorers with incomplete snapshots of ecosystems that exist beyond human reach. Engineers often describe this as partial vision, a reminder that the ocean conceals far more than it reveals. Cameras cloud and crack, lights flicker, and communication cables snap, severing contact with the world above and leaving crews in tense silence, aware that the success of months of planning can be undone within minutes. Acoustic signals lag behind commands, creating an unsettling disconnect between pilot and machine, and operators often navigate blind through blackness, relying on intuition and partial sensor feeds. Each descent becomes a suspenseful negotiation. The ocean tests every design, every calculation, and every contingency, revealing the gulf between human expectation and the ocean's unyielding reality. Modern submersibles, like the Nereus and Trieste, illustrate both triumph and vulnerability, showing that even when a mission succeeds, the margin of safety is perilously thin. Every mechanical failure serves as a stark reminder of the ocean's authority, an invisible hand that enforces its limits without malice or pause. Implosions are sudden and catastrophic, leaving only scattered debris and distorted readings for scientists to reconstruct after the fact. Hydraulic systems fail under compression. Power systems falter due to the energy required to withstand dense water, and delicate robotic manipulators become brittle, unable to perform even simple movements. These incidents underscore a sobering truth. The ocean is a sovereign environment that can never be fully tamed by human ingenuity, and every success is measured in increments rather than absolutes. Submersibles designed to explore the Mariana and Tonga trenches endure stresses far beyond laboratory simulations, testing material science in real time. Pressure vessels are engineered to maintain integrity under loads equivalent to thousands of tons pressing from every direction. Yet each dive confronts unpredictable turbulence, sediment flows, and minute structural flaws. Even with redundancy and fail-safes, the reality of the deep ocean exposes weaknesses invisible at the surface, demonstrating that engineering is constrained not by imagination, but by the fundamental laws of nature. Historical accounts of the Trieste's dive in 1960 emphasize how every descent is an experiment in courage as well as science. Pressure-induced implosions, hydraulic malfunctions, and energy depletion underscore that even cutting-edge technology remains provisional against these extremes. Batteries drain faster in the cold, motors strain under compression, and communication relays degrade. Every mission is thus a delicate balance. Operators push machines to their limits to capture data while constantly acknowledging that survival cannot be guaranteed and that even success represents only a temporary victory in a landscape that will continue to challenge every future attempt. The line between discovery and disaster is thin, and even incremental advances demand years of preparation and testing. Remote monitoring and autonomous vehicles provide partial glimpses, yet each descent emphasizes how little can truly be achieved in real time. Acoustic mapping, photogrammetry, and laser scanning capture fragments of trenches, but the results are incomplete mosaics, leaving vast regions unseen. Even the most sophisticated AI-guided landers can document only local areas before battery limits or mechanical failure cut short exploration, underscoring the ocean's persistent inaccessibility and the provisional nature of human understanding in these extreme realms. Each mission feels like opening a tiny porthole into a cathedral of darkness that stretches far beyond perception. Under the weight of unbroken darkness, efforts to map the seafloor with sonar and multi-beam systems produce only partial mosaics, while vast swaths remain uncharted, cloaked in darkness and inaccessibility. Variations in seafloor topography, sediment composition, and water column density complicate even the most advanced mapping technologies, producing data that must be interpreted cautiously. Scientists are forced to infer much from indirect readings, modeling entire sections based on sparse measurements, emphasizing the profound limits of what can be known about these extreme depressions. The ocean constantly reminds humanity that even meticulous planning cannot fully conquer its scale or complexity. Surrounded by the silence of failed missions and wreckage, the ocean conveys a lesson that the deepest reaches are not merely difficult to explore, they are fundamentally resistant, ensuring humanity's understanding will always be partial, provisional, and incomplete. Each shattered hull, every lost sensor, and every malfunctioning camera serves as a testament to the gulf between human ambition and the reality of extreme oceanic environments. The Hadal trenches, already incomprehensible in scale, remain a realm where even our best machines are humbled, leaving observers with a sense of awe and humility and preparing the mind for the deeper challenge of descending into the ocean's final frontiers, where even the boldest technology may fail again. The ocean we cannot map. In the aftermath of machines crushed by pressure and betrayed by failing sensors, the ocean stretches as an uncharted labyrinth, a realm where even our most sophisticated mapping tools offer only partial glimpses of its vastness. Sonar pulses, intended to illuminate hidden contours, strike the seafloor and return fragmented echoes, painting fleeting patterns of valleys, ridges, and crevices that dissolve almost immediately into shadowed ambiguity. What appears as a map is more a provisional sketch, an approximation of reality, where every data point is a negotiation between human expectation and the ocean's ceaseless motion. The Hadal trenches, once glimpsed through shattered cameras, remain a testament to scale and unpredictability, reminding us that even when we chart, we do not truly know. Beneath this darkness, sediment flows silently, slipping along continental slopes and abyssal plains in currents invisible to the human eye. Turbidity currents, surging with the weight of countless tons of silt, sand, and organic debris, carve ephemeral channels and alter landscapes faster than instruments can record. These flows may travel hundreds of kilometers, reshaping seafloor topology and erasing previously mapped features in moments, leaving scientists to reconstruct events from subtle sedimentary clues. Each shift underscores the ocean's dynamism, emphasizing that no snapshot, no matter how precise, can capture permanence in a place where the floor is as alive as the water above it. Internal waves ripple through layers of seawater, bending acoustic signals and creating distortions in sonar imaging that challenge assumptions of stability. These unseen oscillations, moving at speeds of tens of centimeters per second over hundreds of kilometers, subtly rearrange water density and temperature gradients, making mapping a game of guesswork and correction. Even the most sophisticated ROVs and autonomous survey vessels must contend with these fluid movements, which blur the line between structure and motion, ensuring that cartography remains an act of partial comprehension rather than total understanding. Multi-beam sonar systems, celebrated as the pinnacle of ocean mapping, reveal the seafloor in astonishing detail, yet remain bound by limits imposed by physics and scale. Each beam of sound covers only a narrow corridor, leaving the vast majority of the abyssal expanse untouched in every mission. Computational models attempt to interpolate the gaps, generating mosaic-like maps, but the resulting images are approximations, blending measured reality with educated assumptions. The deeper and more dynamic the terrain, the greater the uncertainty, transforming every map into a portrait of possibility rather than fact. Even tectonic activity conspires against comprehensive mapping. Earthquakes subtly shift ridgelines, fracture plains, and trigger underwater landslides that alter landscapes overnight. Mid-ocean ridges slowly rise and fall, and hydrothermal systems deposit chimneys of mineral matter in patterns unpredictable in time and space. As a result, maps become obsolete almost as soon as they are created, requiring constant updating that even the most sophisticated monitoring networks cannot fully achieve. The ocean's geography is fluid in a geological sense, resistant to the permanence human minds naturally seek. The sheer scale of the seafloor amplifies these challenges. Abyssal plains span thousands of kilometers, a silent expanse of near uniform darkness, where a single survey covers only a fraction of the territory. In these immense stretches, even repeated passes by multiple ROVs and sonar systems leave blind spots, uncharted crevices, and unobserved canyons. Human effort is dwarfed by the ocean's magnitude. The deeper we attempt to know, the more vast and unknowable it becomes, and every mapped area serves as a reminder of the immense gaps between measurement and reality. Turbidity flows, internal waves, and shifting sediments are not merely obstacles to technology, they are active participants in shaping the seafloor. And they remind scientists that the ocean resists human categorization. Features recorded one month may vanish the next, eroded or buried under layers of new deposits. As a result, even continuous monitoring produces a dynamic picture, a seascape in motion where permanence is an illusion. The ocean does not preserve its features for observation. It lives independently of our curiosity and instruments. Mapping reveals only the terrain, but within that terrain lie cryptic habitats that remain invisible even when the ground itself is known. Canyons, fissures, and slopes conceal entire ecosystems that exploit microcurrents, sediment pockets, and mineral deposits invisible from above. Creatures adapted to these niches may never be observed directly, even by ROVs designed to survive crushing depths, and life continues in complex networks beyond human perception. The partially mapped ocean thus becomes both a geological and biological mystery, its surface in data revealing far less than the processes and life it shelters. Even in areas partially charted, scientists must rely on inferential reasoning and indirect observation, combining sonar, sediment cores, chemical sampling, and glimpses from submersibles to piece together the larger picture. Yet this patchwork understanding is provisional, forever limited by the ocean's fluidity, darkness, and scale. Each success in mapping is a fragment of truth. Each failure reinforces the profound humility required when confronting a world that cannot be fully known. The process itself becomes a meditation on limits, patience, and the acceptance that some aspects of nature remain irreducibly hidden. And so, as the last sonar pulses fade into uncharted darkness, it becomes clear that mapping the ocean is not merely difficult, it is fundamentally impossible in totality. Every current, every sediment shift, every tectonic tremor, and every unseen organism ensures that the seafloor remains a landscape of partial knowledge, a constantly evolving mystery. While technology provides fleeting glimpses of form and structure, the ocean retains dominion over scale, movement, and hidden life, inviting reflection on the humility of human ambition and preparing the mind for the unseen biological mysteries that persist even where the terrain has been tentatively traced. The invisible majority. Tucked into the hidden layers of the seafloor, an unseen universe thrives. Its billions of inhabitants invisible to the naked eye, yet staggering in abundance, silently orchestrating the foundations of ocean life. Each granule of deep-sea mud shelters microbial communities adapted to extremes of pressure, darkness, and chemical scarcity, functioning in ways that are foreign to shallow water understanding. These microorganisms, often no larger than a single micron, constitute the bulk of oceanic biomass, operating in layers that humans have only begun to glimpse through drilling cores, metagenomic sequencing, and chemical proxies. Their existence renders the ocean simultaneously more alive and more unknowable, because the very life that dominates the planet cannot be observed directly or fully quantified, a fact that continually humbles oceanographers and challenges our assumptions about what life truly encompasses. Within sediments, microbial populations form dense mats and filamentous networks that facilitate chemical exchange and nutrient cycling, creating microhabitats that sustain further life. Chemosynthetic bacteria harness energy from minerals, hydrogen sulfide, and methane, performing photosynthesis's functional equivalent in utter darkness. They drive elemental transformations of carbon, nitrogen, and sulfur, processes that ripple outward to influence ecosystems tens of meters above the seafloor and even affect global biogeochemical cycles. Despite their minuteness, these communities operate on scales far beyond human perception, their collective activity shaping entire vent ecosystems and abyssal plains alike, quietly engineering the conditions for life in extreme environments while remaining almost entirely imperceptible. Genetic analyses have revealed a staggering diversity that far exceeds prior expectations. DNA sequencing uncovers thousands of unique microbial lineages per cubic centimeter of sediment, each equipped with biochemical strategies optimized over millions of years. Extremophiles thrive under pressures that would crush human-designed vessels, metabolizing compounds that exist only in chemically isolated pockets of the deep biosphere. This invisible majority, through its diversity and adaptability, exemplifies the resilience of life in conditions considered inhospitable, reminding observers that our conception of habitability is inherently shallow. Each microbial genome sequenced hints at an evolutionary history that predates much of the visible ocean life, offering a chronicle written in biochemical codes rather than fossilized shells. These microorganisms often organize into intricate architectures, biofilms that coat rock surfaces, and filamentous colonies that span sediment layers. In doing so, they alter local chemistry, mediate mineral deposition, and influence sediment stability. Their metabolic activity converts inorganic compounds into energy usable by other organisms, creating micro-ecosystems within an environment that appears inert to the untrained eye. Even subtle movements of water or sediment barely disrupt these colonies, and their persistence across millennia suggests a form of ecological engineering beyond immediate human comprehension, operating quietly and steadily in the abyss while humanity peers at the ocean with fleeting glimpses of curiosity and ambition. Microbial mats are not alone. Viruses and phages pervade these environments, regulating population densities, driving evolution, and orchestrating cycles of biomass turnover. Viral lysis releases nutrients into the surrounding sediment, feeding neighboring bacteria in a cycle both invisible and vital. This constant, unseen interplay shapes genetic diversity and ecosystem stability, silently sculpting life across the deep biosphere. Every cubic centimeter becomes a universe of interaction, largely decoupled from surface observation yet fundamental to the ocean's broader function, a reminder that life is often more intricate and interdependent than our senses or instruments can capture. Movements within the seafloor add layers of complexity. Turbidity currents, slow slumps, and micro-movements shift microbial habitats, forcing communities to adapt or disperse. Even in the cold, oxygen-depleted layers of the abyss, bacteria demonstrate remarkable flexibility, surviving in chemical gradients, anaerobic pockets, and mineral-rich fissures. Such persistence illustrates that life is not only abundant, but supremely resourceful, able to exploit every available niche, however marginal. The ocean's floor is therefore less a static foundation than a living, shifting matrix of microbial ingenuity, quietly resisting observation and redefining notions of ecological stability. Quantifying this hidden biomass presents profound challenges. Estimates suggest that microbes in the deep biosphere outnumber all visible ocean life by orders of magnitude, yet their actual populations remain largely inferred rather than observed. Metagenomic studies provide sequences but cannot fully reconstruct functional interactions or spatial arrangements. Sediment cores offer snapshots, but each core represents a fraction of a dynamic system, leaving vast stretches entirely unexamined. Even the most sophisticated modeling and predictive algorithms rely on partial data, emphasizing that human comprehension is necessarily fragmentary in the face of such invisible magnitude. Though unseen, the impact of these organisms is monumental. Deep biosphere microbes drive carbon sequestration, mediate nutrient availability, and underpin life in hydrothermal vent ecosystems. Without them, chemosynthetic vent communities would collapse, and the biogeochemical balance of the oceans would shift. In essence, the invisible majority does more than survive. It sustains the ocean as a planetary system, performing processes that ripple outward to affect surface waters and, ultimately, climate systems on Earth. Their silence and minuteness belie their planetary significance, a quiet yet fundamental rule of life that humans are only beginning to recognize and understand. Every glimpse obtained through cause, sequencing, and chemical analysis is fragmentary, offering only hints of the full story. Scientists can infer presence, metabolic pathways, and potential interactions, yet the real dynamics, the timing of growth, predation by viruses, and ecological feedback remain largely hidden. The ocean's dominant life forms operate beyond the reach of direct observation, creating an invisible architecture upon which the observable ocean depends. Each discovery deepens wonder, while reinforcing the recognition that much remains unknowable, an enigmatic majority that governs the conditions of every visible and measurable phenomenon above. Whenever technology sheds light on larger, fleetingly visible organisms, macrofauna, gliding through the water column, or vent communities glimpsed by ROVs, the microbial majority persists silently beneath, a hidden foundation that dwarfs any surface life in sheer abundance and significance. This invisible majority reminds us that the ocean is not simply vast in size, it is profoundly complex in form, dominated by life that exists entirely outside our direct sensory perception. The transition from unseen microbes to rare, observable creatures foreshadows the next layer of mystery, a deep biosphere intertwined with ephemeral life forms, hinting that the ocean's most consequential inhabitants are also the most elusive, perpetually defying the human desire for total comprehension. Creatures revealed only once. Occasionally, the quiet depths are pierced by a sudden shimmer, a creature glimpsed once before vanishing into shadow, as if the ocean itself allows only a fleeting acknowledgement of its inhabitants. A giant squid glides past, its elongated tentacles drifting like wisps of smoke, momentarily outlined against the faint luminescence of abyssal waters, before disappearing entirely from view. Such encounters are rare, often captured by ROVs or deep-sea cameras baited for weeks, yet their rarity is not merely a consequence of human limitations. It reflects a fundamental strategy of survival in a world where visibility is a liability. Every motion, every reflective scale or bioluminescent flicker becomes a momentary signature, leaving the observer with more questions than answers and a profound sense of the ocean's elusiveness. A gulper eel appears next, its cavernous mouth a grotesque silhouette against a faint green glow produced by scattered bioluminescence. This moment, though brief, offers insight into adaptations honed over millions of years. Slow metabolisms to conserve energy, distensible stomachs to exploit rare prey, and eyes tuned to capture the faintest trace of light. Observers note the rhythmic undulations of its elongated body, a movement both deliberate and efficient, optimized for a realm where every joule of energy is precious. Such creatures challenge conventional definitions of abundance and presence, existing largely outside the human ability to measure or catalogue, their lives a series of vanishing points across the vast darkness. Camera traps reveal patterns invisible to the human eye, capturing ghostly siphonophores that shimmer like fragile chandeliers drifting through a black void. Their colonies stretch for meters, yet their motion is subtle, synchronized with currents and chemical gradients that only they detect. Each frame captured is a fragment of an ecological narrative, that will never be fully reconstructed. These organisms appear as transient phantoms, offering the illusion of presence while retaining ultimate mystery. Observers can note morphology, length, and coloration, but behavior, social interaction, and lifespan often remain speculative, emphasizing the limits of observation in an environment that exists almost entirely beyond human perception. These fleeting encounters underscore the unpredictability of life in extreme depths, where survival demands stealth, patience, and exquisite sensitivity to chemical, tactile, and hydrodynamic cues. Many species are solitary, appearing only to feed, migrate, or reproduce, their timing synchronized to environmental triggers imperceptible to outsiders. Even the most sophisticated tracking equipment cannot follow them for long. The creatures slip past the gaze of human instruments with the ease of a phantom, leaving behind only traces of disturbed sediment, fleeting shadows, or bioluminescent glows that vanish almost instantly. In these moments, the observer realizes that the ocean's macrofauna do not exist on human terms, and that the very act of observation may itself be an intrusion into their carefully balanced world. Every brief sighting is accompanied by questions that may remain unanswered for decades. How many of these organisms exist? What are their population dynamics, reproductive cycles, or interspecies interactions? Observers can piece together clues from the patterns of repeated sightings or the composition of stomach contents recovered opportunistically, but the true breadth of diversity remains elusive. Even statistical models, informed by deep-sea trawls and sonar readings, yield estimates with margins so large that the results feel almost philosophical, a reflection of humanity's partial grasp on a realm defined by invisibility. Some species appear only to perform critical life functions in specific microhabitats, vanishing immediately afterward. Vertical migrators, such as certain deep-sea shrimps or lanternfish, traverse hundreds of meters each night, crossing layers of water with varying temperature, pressure, and light intensity. They ascend briefly into zones where detection is possible, then descend into darkness where sensors cannot follow. This ephemeral presence magnifies the difficulty of cataloguing them and highlights a biological paradox. The creatures most abundant in the ocean's depths are often those we can see least, defying our expectation that visibility correlates with significance. Depth, pressure, and darkness combine to create an environment where stealth is not just advantageous, but essential. Some predatory species exploit low light conditions to ambush prey, while others maintain translucent bodies to blend with the inky blackness. Bioluminescence is employed sparingly and strategically, as a lure, a signal, or a sudden flash to disorient attackers. The fleeting nature of these illuminations underscores the transience of human observation. Moments of light captured by submersibles are temporary windows into a world that rarely consents to be fully revealed. Even with repeated submersible missions, the majority of deep-sea macrofauna remain invisible. Occasionally, a ROV will capture footage of a new species, its appearance recorded in a few seconds of grainy video before it vanishes into the darkness. These instances provide tantalizing glimpses into previously unknown morphologies, elongated limbs, gelatinous bodies, and strange appendages adapted to the abyss, but they are insufficient for comprehensive study. Researchers can propose hypotheses about feeding habits, reproductive strategies, or evolutionary lineage, yet these remain conjectures, illustrating that much of the deep-sea ecosystem is perpetually beyond classification. The ephemeral nature of these creatures also emphasizes the ocean as a record of impermanent moments where life is transient, interactions fleeting, and ecosystems persist largely unseen. Each observation, no matter how brief, contributes to a growing database of knowledge, while simultaneously underscoring how little is truly known. The ocean's depths become both a living archive of current biological processes and a repository of evolutionary adaptations that continue to unfold in obscurity, revealing that the act of witnessing is inherently incomplete, partial, and provisional. These ephemeral glimpses hint at a broader narrative. The deep ocean is not merely vast in volume, but profoundly resistant to human comprehension. Life here does not conform to schedules, visibility, or patterns that can be easily quantified. Instead, it thrives on impermanence, evasion, and adaptation. The fleeting creatures we catch on camera or observe through submersibles exist as reminders that the ocean stores its most extraordinary stories beyond reach, where even our best technology can only provide hints. The transition from these transient macrofauna to the ancient, hidden archives preserved in sediment and chemistry below foreshadows the next revelation, the ocean as a living memory, holding the echoes of epochs, environmental shifts, and biological lineages that we may never fully witness. The memory of water. Lurking below the transient displays of oceanic life, a slower, more deliberate story unfolds, written not in motion or flesh, but in the currents that pulse through the global ocean. These massive flows, invisible to the human eye yet relentless in their progress, carry heat, salt, nutrients, and chemical traces across thousands of kilometers, threading together the surface, mid-water, and abyss in a vast living network. The thermohaline circulation, often described as the ocean's conveyor belt, moves water masses over centuries, transporting warmth from equatorial regions toward the poles while sending dense, cold water toward the depths, creating a rhythm both ancient and ongoing, imperceptible yet omnipresent. Temperature gradients slice the ocean into layers, each directing currents along paths that are invisible but decisive, guiding the distribution of life and the flow of energy. Surface winds tug at the uppermost layers, initiating waves and gyres whose effects cascade downward, imprinting motion on water masses hundreds of meters below. These currents, while seemingly uniform at the human scale, carry hidden eddies and spirals, minute vortices that trap plankton, nutrients, or chemical markers and transport them over vast distances, acting as nature's own long-distance couriers. Salinity and dissolved oxygen converge in complex patterns, encoding centuries of environmental change. Water that sinks near Greenland or Antarctica carries with it the thermal and chemical signature of the surface at the time of its descent, essentially locking away snapshots of climate and atmospheric conditions for decades or centuries. Within these moving archives, oxygen minimum zones mark areas of persistent scarcity, guiding the distribution of deep-sea species while recording the intricate interplay between biology, chemistry, and global circulation. Every drop is a messenger of history, every density current a ledger of Earth's climatic memory. In the depths, the whispers of ancient climates persist, carried silently in water that may have travelled halfway across the globe before resurfacing in a new hemisphere. Trapped gases, dissolved nutrients, and isotopic ratios provide scientists with a molecular archive. Yet these signals are partial and scattered, revealing patterns only when interpreted across decades of measurement. Paleoclimate reconstruction relies on understanding these flows, yet even the most precise instruments can only capture fragments of the full narrative, leaving a sense that the ocean itself remains the ultimate arbiter of memory. Water masses, once set in motion, travel across basins, threading a web older than most human civilizations. The Antarctic bottom water slowly fills trenches, while North Atlantic deep water traces its path along continental margins, creating a dynamic circulation that shapes climate and oceanic chemistry alike. As the ocean moves, it maintains connections between disparate ecosystems, transporting larvae, nutrients, and detritus across continents, often linking surface processes with abyssal communities. These movements, slow yet inexorable, create a continuity that human observers can glimpse only intermittently, a constant flow that renders the ocean simultaneously knowable and unknowable. Life within this vast conveyor is guided by the memory encoded in water itself. Plankton bloom where nutrients are brought to the sunlit surface by upwellings. Deep-sea species follow the oxygenated currents or trace chemical gradients to feed and reproduce. Even the most isolated organisms are bound to these invisible highways, which dictate the availability of energy and the timing of ecological interactions. The ocean, in this sense, is both archive and choreographer. It stores the past while orchestrating life in the present, all beyond the full comprehension of human senses or technology. Occasional disruptions, eddies, internal waves, or abrupt changes in current speed reveal the ocean's capacity for impermanence within constancy. These ephemeral features may last days or months, reshaping nutrient pathways, mixing oxygen levels, or redirecting larvae. Their transient nature contrasts with the slow, measured circulation beneath, emphasizing the ocean's dual character, persistent yet flexible, ordered yet chaotic. Observers may record these phenomena, yet each measurement is a snapshot in a system that refuses stasis, reminding us that no single moment can capture its complexity. The ocean also carries echoes of atmospheric events, from sudden storms to centuries-old shifts in wind patterns. Surface waters influenced by monsoons, trade winds, or cyclones transfer their energetic and chemical imprints downward, where they are diffused and stored in colder, denser layers. These movements create a palimpsest, a record of change and adaptation that is constantly overwritten yet never erased. Understanding this memory requires both patience and humility, as the ocean archives events in ways that are impossible to fully reconstruct from a single vantage point. Human attempts to track this memory, from drifting buoys to autonomous floats, reveal both the sophistication of technology and its limitations. Instruments measure temperature, salinity, dissolved oxygen, and current velocity with increasing precision, yet they cannot replicate the centuries-long journeys of water masses or the subtle chemical fingerprints encoded in their depths. Each deployment is temporary, each data set a fragment, and despite our advances, the ocean retains dominion over its own narrative, ensuring that total comprehension remains out of reach. Across the endless cycles of activity and stillness, the ocean asserts a lesson about the limits of human perception and intervention. Its currents carry the weight of eons, transporting climate, chemistry, and nutrients across the globe, while remaining largely imperceptible to those who stand on its shores or peer from submersibles. The water remembers what humans cannot fully measure, connects what humans cannot easily see, and persists where observation is incomplete, preparing the mind to accept that no matter the tools or ambition, the ocean will always hold secrets beyond our reach. As our gaze moves forward, the memory of water leads naturally to the realization that even within these currents, life, adaptation, and history intertwine, and the next mysteries of the deep await places where light has vanished entirely, and the rules of the surface world no longer apply. The threshold humans cannot cross. As our gaze drifts downward from the ocean's memory, the comforting undulations of currents and the slow whisper of water give way to an oppressive, tangible darkness that human bodies cannot endure. Each meter deeper intensifies a weight unseen yet relentlessly felt, a hydrostatic pressure that compresses every cavity, every organ, and every fragile vessel humans inhabit. In these depths, lungs that sustain life on the surface would collapse instantly, bones would fracture under the invisible squeeze, and blood would congeal in defiance of survival. The ocean, in this arena, is indifferent to ingenuity. It tests the human form at scales for which evolution has never prepared us. A realm that reshapes assumptions about physiology, endurance, and vulnerability with each meter fallen. Engineers have crafted marvels of material science to bridge the abyss, from titanium spheres capable of withstanding over 1,000 atmospheres of pressure to syntactic foams designed to resist implosion while housing the lights, cameras, and instruments that extend our perception. Yet even the most sophisticated hulls groan under the weight of the sea. Each descent a delicate negotiation between strength, buoyancy, and the relentless law of physics. Every joint, every seal, and every pressure-resistant window is a battlefield where failure is catastrophic, a reminder that even the best design offers only a reprieve. The history of deep-sea exploration is littered with lost submersibles, snapped tethers, and crushed hulls, each serving as a silent witness to the ocean's uncompromising nature. Oxygen supply, temperature regulation, and structural integrity converge in a fragile equilibrium, a narrow corridor where human ambition meets natural extremity. Life support systems tick and hum, monitoring and compensating for conditions the human body cannot tolerate. Yet all these mechanisms remain tethered to contingency. One breach, one miscalculation, and the abyss is absolute. The human element is secondary to physics. A momentary distraction or misread gauge can end a mission before it begins. As submersibles inch downward, the tension is palpable, a quiet acknowledgement that the boundary between curiosity and catastrophe is measured in millimeters of metal and seconds of human oversight, and that even the most prepared explorers remain at nature's mercy. Cameras flicker to life, piercing the immediate gloom, yet even these mechanical eyes capture only infinitesimal slices of the vast darkness beyond. For every illuminated trench wall, thousands of unseen meters remain inaccessible. Corridors of shadow where no human, no sensor, no light can endure. Life exists here in a delicate dance of survival against pressure, temperature, and scarcity. Yet our machines glimpse only the edges to fragments of a reality that surpasses comprehension. Every captured frame is a fragmentary narrative, teasing the mind with shapes and movements that vanish before understanding can catch them, leaving curiosity suspended in a void that defies conclusion. Even within the most robust remotely operated vehicles, turbulence, falling sediment, and jagged topography challenge assumptions, reminding observers that exploration is provisional. Tethered to surface support or autonomous programming, these machines confront a world that does not yield. It bends and shifts beneath them, offering fleeting glimpses before retreating into obscurity. Each successful descent becomes a testament not only to engineering brilliance, but to the immutable limitations imposed by the environment itself. In the deepest trenches, equipment may operate at the limits of material science, with every mission calculated to the finest degree, and yet uncertainty persists, a silent participant in every maneuver. Organisms adapted to these extremes further underscore human inadequacy. Deep-sea fish with flexible skeletons and compressible tissues, giant amphipods, and other and Haddle-adapted fauna inhabit zones lethal to humans, thriving where every surface norm collapses. Bioluminescent signaling, slow metabolisms, and unique reproductive strategies illustrate a resilience that our biology cannot emulate. Observers witness existence that defies conventional expectation, yet even these sightings are transient, recorded in seconds of footage that vanish as quickly as they appear, leaving questions unanswerable and mysteries intact. These fleeting encounters remind us that life in the deep is a continuous negotiation with extreme conditions, one entirely removed from the frameworks that govern the surface world. Even theoretical models, built on decades of careful observation and experimentation, fail to predict every nuance of this extreme environment. Currents ripple in patterns unrecorded, sediments shift unpredictably, and unseen obstacles challenge every assumption. Thermal gradients, geochemical anomalies, and microscopic detritus interact in ways that confound expectations, demonstrating that even abstract understanding cannot substitute for direct presence, a presence the human body is physically barred from attaining. The deeper the descent, the more the gulf between knowledge and reality widens, emphasizing the vastness, not just of space, but of human ignorance when confronted by a system beyond direct experience. Surface tethering and remote monitoring highlight the dependence of humanity on intermediaries, be they cables, machines, or algorithms, to glimpse even the outer edges of these depths. Each probe is a lifeline, every remotely operated camera a fragile eye into a world inhospitable to human flesh. Submersibles are extensions of human intention, not the body itself. They are instruments of translation, converting light, motion, and pressure into data humans can interpret. The observer realizes that direct presence is impossible. Survival is contingent, observation is mediated, and understanding remains incomplete. In the interplay of physics, biology, and technology, the ocean asserts a quiet dominion. The deepest trenches, the steepest slopes, the dark corridors beyond light's reach, these are realms untouched by human hands, almost entirely immune to our instruments. For all our machines, all our calculations, and all our ambition, certain territories remain mathematically and physically unreachable. Even the most sophisticated ROVs and autonomous vessels are humbled by conditions that humans cannot survive, and these outer limits remind us that there are frontiers in the natural world no technology can ever fully conquer. Ultimately, this descent into the ocean's outer edge reinforces a profound humility. We confront our fragility, our dependence, and our limits in a realm where survival is mediated entirely by metal, algorithms, and the ingenuity of others. The threshold humans cannot cross is not a line, but an infinite gradient, a reminder that no matter our advances, some worlds will remain forever beyond reach, whispering secrets that can only be imagined, never possessed, and that the deep ocean, in all its complexity and darkness, will always hold truths inaccessible to human experience. Here, at this final frontier of human proximity, the ocean asserts a singular truth. Mastery is an illusion. Presence is provisional, and some depths will remain an eternal mystery, the forever unexplored. The abyss stretches in gradients of shadow and pressure, each meter a boundary humanity cannot hope to cross. Even with the most advanced submersibles and autonomous vehicles, our reach is limited to fleeting glimpses, and much of the seafloor remains a landscape of conjecture. Trenches plunge tens of kilometers beneath the surface, their walls carved by tectonic collision and erosion over millions of years, yet the vast majority of these extremes have never been seen by human eyes. Every descent confronts engineers and scientists with the same immutable truth. The deeper we attempt to go, the more the ocean asserts its inaccessibility. Layers of ancient sediments conceal trenches, ridges, and faults that no probe can permanently catalogue. Turbidite flows, avalanches of sand and silt cascading down slopes, erase traces of prior mapping within hours or days. Even the most precise sonar scans capture only temporary impressions, shadows of the moving seafloor rather than fixed topography. Vast abyssal plains, seemingly monotonous, shift over geological timescales, demonstrating that the landscape itself is a moving target, forever out of reach of definitive human records. Each mapped canyon may vanish into obscurity, replaced by newly deposited silt or altered by subtle tectonic uplift, reminding explorers that permanence is an illusion. Time moves differently here, unmarked by clocks or calendars, recorded only in geological slow motion. Sediment accumulates at rates, often measured in millimeters per millennium, while hydrothermal vents reshape localized terrains in sudden bursts. This contrast between imperceptible accumulation and abrupt geological upheaval complicates attempts to create coherent maps, leaving even long-term research programs reliant on extrapolation, probability, and partial observation. Humanity can log coordinates and elevations, but the ocean resists being frozen into a static representation, as if it actively resists being fully known. Instruments falter, corroded by salt and crushed under weight, leaving the majority of the seafloor invisible. Pressure at the deepest hadal trenches exceeds 1,000 atmospheres, and every hull and sensor must contend with forces that can bend, rupture, or implode machinery within seconds. Cameras and lights illuminate only minuscule fractions of the surrounding terrain, while electronics are prone to catastrophic failure in conditions that are routine for native organisms. For every successful dive, dozens more end in incomplete data or lost equipment, emphasizing the provisional nature of human knowledge in this realm and reinforcing the humbling scale of the unknown. Echoes of sound return distorted, hinting at structures both massive and mercurial, impossible to map in full. Even modern multi-beam sonar, which can scan wide swaths of seafloor, struggles to account for the interplay of water density, temperature gradients, and fine sediments that absorb or scatter signals. Subtle undercurrents and internal waves refract sound unpredictably, leaving gaps in coverage and creating illusions of continuity where none exists. Each pulse of energy reaches only a fraction of the unknown, reinforcing the ocean's impenetrable scale and the futility of seeking a complete picture. Currents weave through voids, shifting sands, and nutrient flows faster than any survey can register. Hydrothermal plumes, turbidity currents, and abyssal jets carry particles for kilometers, continuously modifying the seafloor environment. Rift valleys, fracture zones, and sediment slides reshape topography silently and invisibly, so that even areas mapped years earlier may have altered before human instruments return. The ocean asserts a dynamic memory, recording change on its own terms rather than ours, leaving explorers to navigate a landscape that is at once familiar and alien with each return. Even when glimpsed, the outlines of creatures and formations dissolve as quickly as they appear. Rare species observed by deep-sea cameras vanish beyond the reach of tracking equipment, and microbial mats and vent communities can shift composition in hours. For researchers, the biological environment becomes a moving tableau, a mosaic of life that cannot be fully predicted or catalogued. Each encounter, however brief, underscores the tension between human curiosity and the ocean's self-contained processes, emphasizing that knowledge is always provisional, fleeting, and fragmentary. The mind struggles to comprehend distances measured in kilometers of unknown, unlit expanses. Challenger Deep, the Mariana Trench, spans nearly 11,000 meters in depth. Yet similar abyssal depressions remain entirely unexplored. The horizontal scale is equally daunting, with vast plains extending thousands of kilometers between ridges and trenches. Cognitive limits amplify the challenge. Our perception cannot easily grasp the immensity, and our tools, no matter how advanced, provide only localized snapshots in a sea of perpetual obscurity. Data collected over decades reveals patterns, yet each discovery opens more gaps than it fills. Maps of seafloor topography remain incomplete, and estimates of species distribution or chemical flux are provisional. Even the most sophisticated modeling relies on assumptions drawn from a fraction of actual measurements, emphasizing that knowledge of the ocean is always probabilistic. For every new canyon, vent, or abyssal ridge uncovered, there are countless features remaining unobserved, a stark reminder that the ocean is a living, shifting frontier, ungoverned by human expectation. Our limitations extend beyond observation. They touch cognition and imagination. The deep ocean is a landscape of extremes, where even conceptions of distance, time, and scale falter. Each descent demonstrates the gap between human perception and environmental reality, highlighting how provisional every measurement, every image, and every observation truly is. The ocean challenges not only instruments but the very frameworks we use to understand it, defying attempts to impose completeness or certainty upon its shifting forms. From abyssal plains to towering mid-ocean ridges, the ocean preserves its dominion, a realm whose immensity ensures that mystery is eternal. No matter how powerful our technology becomes, full exploration is mathematically and physically impossible. The very act of mapping alters conditions, and the sheer vastness, coupled with constant change, guarantees that large portions will remain unseen for all time. Humanity may illuminate fragments of this world, but the greater ocean will persist as an uncharted, unknowable expanse, a reminder that some frontiers are eternal and some truths forever beyond our grasp. In the darkness, the seafloor whispers of permanence and change alike, leaving only imagination as a bridge to what cannot be visited, known, or possessed. The ocean withdraws like a patient guardian, its secrets intact and indifferent to our curiosity. Every descent, every fleeting glimpse, reminds us of the vastness that humbles human ambition and imagination alike. We leave the depths not with mastery, but with awe, a recognition that some worlds are meant to remain untamed, eternally beyond reach. In the quiet darkness, life, time, and mystery persist on their own terms, indifferent to our presence. As the surface reclaims the light, we carry the ocean's silent lesson. Wonder is infinite, and some depths will never yield their truth. If you enjoyed this journey, consider liking, subscribing, or sharing your thoughts in the comments below.